I already put it on reserve for 24 hours. So no one can keep it for no longer than a day. Okay. All right. So let's talk about the strike. So if the strike happens, again, we continue as usual. All right. Because of course we've been doing things online. So we continue to do things online. The only thing is from what I've heard, email is still available. I think Zoom is still available. That's true. So we may not be able to access eClass. So that's why it's very important. If you have a web browser in front of you, go to the eClass web page of the course. Okay. All right, go to the eClass web page of the course, and then, okay, so you see here at the beginning of the course, there's a link here. All right, click on that link, please. I think I told you this from the beginning. So this is a web page outside of eClass. So please bookmark this page right now immediately. So if a strike happens, this is where I will post announcements, lecture notes, homework, everything will be here. All right. Okay, so so everything will be here. All right, so please bookmark the page. Okay, so any question about the strike again? Any question? Okay, so again, what other resources? I don't know what other resources that will be locked, but I know that I don't need eClass for the course. All right. I don't need eClass for the course. Okay, so I mean, before the pandemic, I've used web pages like this for my courses, not eClass or Moodle, because usually there were many problems with Moodle at that time, and many times Moodle was down and students were not able to access the course material. So I only used this kind of web page before the pandemic. So I continue to do it now. Samyak asked a very good question. You will not be on strike. Okay, I mean, I support my colleagues to get better benefits, but at the same time, I think students should be my first priority because we've gone through a pandemic. You've lost so many things, so much time. So I think this is your last year. You should be able to finish the course and graduate, right? So in 2016, there was a strike, not faculty strike, it's TAs, teaching assistants and graduate students. I was able to complete the course without TAs, right? Without any TA. I was able to complete my courses at that time without any TA. So this time it's even better than that because I still have my TAs, all right? It's just that they had to work a bit more. So they had to mark, let's say, the homework manually instead of using eClass, but we'll continue as usual, right? So we will try to finish the course so that you can graduate, all right? The only thing that I don't have control over is the final exam, all right? The final exam, okay. So that's we have to wait until it's scheduled and then we make the decision. So Rushi has a question. I also that the strike happens, professors are not allowed to teach in any format either. I'm not sure if that is a problem because I'm not sure. Yeah, to be honest, I don't know because I've never on strike before. I'm in terms of myself as a professor, the last strike from professors was 25 years ago. So I don't know much about if what happens if it's on strike. But in any case, everything will be posted here. I can give office hours, you can read the lecture notes, read textbooks. The last few chapters would be very easy. All right. The last few chapters are easy. You can read the textbook and should be okay. And then I also hope that we don't have to go on a strike, right? Because negotiations are still underway, and I'm optimistic. Okay. Yeah, so I'm not sure about the logistics, to be honest, because I've never been in this situation. But we have all the everything in place. So my suggestion to you is to download everything from eClass, you know, like slides, papers, practice problems, everything on eClass to save on your computer, right? So you can have a material to study for the final exam. Okay, and then we yeah, we go along as we plan. Okay, but from myself, I plan to continue and complete the course to the extent that I'm allowed to do. Okay, all right. Yeah, you're welcome. So of course, yeah, we're not paid during the strike, but that doesn't matter. I in the sense that it's not about the money, it's about other, how can I say, so this time the negotiation is not only about the salary or the money or the benefits, it have other issue as well. For example, workload, equity, and hiring of new faculty. So it's not just about the money. Okay, right. So again, please bookmark this page. All right, we bookmark this page. Now about the midterm tests and the drop date. Tomorrow is the drop date. In theory, you don't need the midterm tests because according to the university rules, you should get 15% of the evaluation by the drop date. So far you have had 15%. Because for the lab you got one lab back, and it's 3.3%, right? 1/3 of 10% is 3.3%. So let's say 3%. And then for the homework and the quizzes, so far we cover 60% of the time, more than 60%, but I consider as 60%. So basically, you already got the feedback for 6/10% for the homework and 6/10 for the quizzes. So if we finish the quiz today, that will be a quiz today. So you get 6% for the quizzes and 6% of the homework. So that will be 12% plus 3% for the lab. So that would be 15%, right? 15%. So you already got 15% to decide whether to drop or keep the course. But I have asked the TA to finish grading by tomorrow morning. So at least we can enter your midterm test marks on eClass. So you should be able to know your mark by around, I would say, noon tomorrow, hopefully, or at the latest in the afternoon tomorrow. So yeah, so that's one thing you should be able to know. If the TA can finish marking by tomorrow morning, the TA, the marker, the grader will leave or may leave. It depends on whether he'll be able to finish by tomorrow morning. He'll leave the papers with Lewin Mo in the lab, and if you come to the lab, you may be able to pick up your paper. All right, you're able to pick up a paper, but I'm not sure. I will post on eClass to let you know whether you can pick up the paper from Lewin in the lab. Okay, there's a question from Dan. What do you mean by drop in the course? So for some students, I don't know because I haven't seen the midterm marks yet. If the grade is too low, then you decide to drop the course so that the course will be removed from your transcript. So you will not see the course on your transcript, all right? so you're not getting a low grade because that could affect your GPA. All right, so that could mean by dropping the course. And if you asked this question, that means you never dropped a course before. So congratulations. No, it's not related to the strike at all. It's related to your performance in the course. All right, it's not related to the strike. It's related to the performance, your performance in the course. Okay. Yeah. All right. So, okay, you're welcome. Oh, so that's good. That means you never dropped a course before. So that's good. Congratulations to you, Dan. All right. Now the midterm marks. I don't know the marks yet. But just in case, if your mark is low, you have to remember that your homework marks and labs, they are very high. So almost everyone got 95 to 100%. All right. So you have to add those and the quizzes to the midterm to decide whether you should keep or drop the course. All right. So don't forget the homework and the right, so the homework and the labs, right? So the labs, I should expect everyone should get 90 to 100%. All right, it's not difficult. They're not difficult. Okay, so don't forget those to add to the midterm test. All right. Okay, so right, so the two lowest quiz marks and homework marks will be dropped in the final grade calculation. Yes. Okay. Okay, the project for 5431, I will send a handout to the graduate students about the project. Okay, I will send a handout to the graduate student about the project. All right. Okay. Any other question about the mark, the drop date, or the strike? Okay. Two quizzes. So I would expect we would have about 8 or 9 quizzes by the end of the course. We'll drop the lowest 2 marks. Okay. And if you missed one quiz, so that quiz could be a 0. So it could be considered the lowest. Okay. So if you missed one quiz, you get 0 on that, then that could be considered the lowest. All right. And we'll drop the 2 lowest marks. Okay. The 2 lowest marks. All right. Any other question about the midterm test and everything? Okay. And in my experience, in the past, usually some students did very badly in the midterm, but they would do better. They did better in the final exam. And I think the reason probably because during the midterm, there were so many tests in the same week or the same day, so they did not have time to study for the midterm. But during the final exam period, the exam was spread out over many days, so they had time to study. Okay, so that's why usually students did better in the final exam than the midterm test, especially for this course because it requires a lot of studying, right? Okay, so just give you some extra information to help you with deciding whether to keep or drop the course. Right. So I hope no one will have to drop the course, but just in case you need to. Right. Okay, so for the quiz, it's about ATCP. All right, the lecture we learned about last time. Okay, all right. Okay, so let's yes. Sure. Right. So yes, yeah. So I answered this question earlier. I think there may have been a problem with the registrar's office. They may, they may, how can I say, missed the course in the request that I sent. So I will send a follow-up later. So to make sure that they will schedule a date for an allocation for our exam. Yeah, no, sorry, no, yes, right. No, I think the registrar office decides the date, not me. right? Usually they decide based on the course enrollment. So, you know, like usually students in the 4th year, they would take these courses, right? So they try to minimize the conflict between those courses. And that's why they make the decision, not me. Yeah. You're welcome. So as soon as I hear from the registrar's office, I will post or send out an announcement about the final exam date. Okay. Right. Yeah, sometimes things fell through the crack and they may miss my request. This term, I sent 2 requests. One was scheduled, one course was scheduled, one exam was scheduled, the other, this course was not scheduled. I don't know why. That's why I said things might have fell through the crack there. Okay. All right, so let's continue with a new topic, which is multi-rate transmission. So again, multi-rate transmission still belongs to wireless ad hoc networks, all right? And then we go to cellular networks in the second hour. Okay, so we get the slide here, okay. All right, okay. So I use the term multi-rate transmissions to make things easier to understand. The research on which the lecture is based they have a paper, and the name is Rate Adaptive Medium Access Control Protocol in Wireless Multi-Hop Networks. It's too long, so I prefer to use multi-rate transmission, but you should remember the title as well. And it's simple in the sense that it's based on IEEE 802.11 Medium Access Control RTS CTS data and acknowledgement. And rate adaptive in the sense that it adapts to the rate. The rate is adjusted to adapt to channel quality. All right, and we use this in wireless multi-hop networks. Okay. All right. So this is the outline of the lecture. We'll take a quick look at multi-rate transmission. Why do we use multi-rate transmission? And then we talk briefly about auto rate fallback. And then we go into the actual research in depth, which is receiver-based auto rate. And then we compare the performance of ARF versus RBAR. And at the end, we summarize the lecture. Okay. All right. So so 802.11 standards, there are many types of standards. So I'm just using one example, which is 802.11b. So with 802.11b, there are 4 transmission rates: 1 megabit per second, 2 megabit per second, 5.5, and 11 megabit per second. Okay. And why do we have many transmission rates? So remember, we talked about before the distance is the distance of the transmission distance is related to the rate. The longer the distance, the lower the rate, right? And why do we concern about these? Because in a mobile ad hoc networks, nodes are moving, so they may be close to each other or they may be far from each other. If they are far away from each other, they should use a low rate. And if they are close to each other, they can use a higher rate for higher throughput. All right. All right. So now there are 2 concepts that we should talk about, which is the modulation scheme, right? So what is a modulation scheme? So, so if you have a computer, the data on your computer is in the digital form, right? In the digital form. Now, if you send a file using 802.11, the digital format of the data will be converted into analog signal, because the waves in the air would be analog signal, right? And that is called a modulation scheme. you encode digital data, bits, right? 0 and 1 bits into analog signal. And the data rate is determined by the number of bits per symbol, all right? And the trade-off is the higher the data rate, the higher the bit error rate. Okay, so we'll see why the higher the data rate, the higher the bit error rate. So let's consider this. If you took 3213, you must have learned about phase shift keying, right? So we would have binary phase shift keying. So in binary phase shift keying, you use two phases, okay? One phase represents bits 1, and other phase represents bits 0, right? So you can see here, the phase indicate that the wave start at this point for bit 1. So for 0, it should be, the phase should be 0 in this case, and this, I believe this is pi, let's say this is pi, right? This is pi. So you can see that 0 and 1 have two different phases, and that indicates that distinguish 0 from 1. So this is another binary PSK, right? They use different phases. Now we can also use more phases. Instead of 2 phases, we can use 4 phases. So this is, you have quadrature phase shift keying. That means you use 4 phases, okay? And if we use 4 phases, you can see 1, 1 start from here, and then 0, 0 start from here, 0, 1 start from here, and 1, 0 start from here, right? So you will have 4 different phases. So if you have 4 different phases, then each symbol can represent 2 bits, right? 2 bits. So you can see here, one symbol here can represent only 1 bit. Now you can have 2 bits. So this gives you higher data rate, right? Because for the same symbol, now you can represent 2 bits. So you have higher data rates. The problem is if there's noise, right? And let's say the noise destroy the first symbol here, you lose only 1 bit. The same noise would destroy 2 bits if you use quadrature PSK, right? Would destroy 2 bits. So that means the higher the data rate, the higher the bit error rate. That you mean you lose more data, all right? So that means if you use high data rate, you must be sure that the channel is good, right? There's little noise, there's little interference. Because if there's a lot of noise, a lot of interference, you lose a lot of data, okay? And you can see this is another example with using multiple bits per symbol. So in this case, we combine PSK with amplitude shift keying. So we can have one symbol now can represent 4 bits, right? Instead of 2 bits as before, now it can represent 4 bits. And you can see here that if now one symbol like this, you have 4 bits. If there's a noise or interference, you lose 4 bits instead of 2, right? So that's why we have to be careful when we use higher rates. We have to make sure that the channel quality is good, otherwise we lose a lot of data, okay? Right, so, all right, so, and, okay, and this diagram here shows the trade-off between data rate and distance, okay? Okay, so in this diagram, we have binary phase shift keying. That's what we've seen before, right? So basically this scheme here. And then we have a quadrature PSK. Basically, this scheme here, all right? And so this, if you use PSK, you can achieve 1 megabit per second. If you use QPSK, you get 2 megabits per second. And it makes sense, right? Because now for every symbol you can represent 2 bits, so the rate is double. With quadrature amplitude modulation, 16 means you can have 16 combination. That means 16 possibility, 16 combination exactly. That means you can represent 4 bits per symbol, right? 16 combination means 4 bits per symbol. Again, QAM 64. Again, 6 bits per symbol. So 6 megabits per second, and 256 combination, that means 8 megabits per second. All right. And you can see here this line. So in this graph, the x-axis represent the distance, and the y-axis represent the mean throughput, right? The mean throughput. So you can see that the throughput for the lowest rate is about here. Okay. Now it doesn't go up to 1 megabit per second. You see it's slightly below 1 megabit per second because we have overhead as well. Remember, we have RTS, CTS acknowledgement, right? So that's why we cannot go up to 1 megabit per second. We go up to only I could say 850 here. Okay. And if the distance is less than 250 meters, that means the quality, the channel quality is good. So you always get this 850 kilobits per second, right? But as soon as the distance hits 240, maybe 240, the throughput will go down, right? Because now you will lose a lot of packets. You lose a lot of packets because the distance becomes farther and farther away. So you lose lots of packets. So the throughput would go down, right? To 0 here. That means at 300 meters, the sender and receiver cannot communicate anymore because they're too far away, right? And similarly for QPSK, it's 2 megabit per second, right? But in practice, I think we achieve only about 16, right? 17, 18, yeah, about 1500, or 1.5 megabit per second only. Again, because of the overhead, RTS, CTS acknowledgements, right? And remember, with RTS and CTS, you have to send at the lowest rate, okay? When even if the data packet can send at 2 megabit per second, okay? Even if the data packet can send at 2 megabits per second, RTS and CTS must be sent at 1 megabit per second, the lowest rate, okay? All right, so my question to you, why do we send RTS? We have to send RTS and CTS at the lowest rate. Anyone? Why do we have to send RTS and CTS at the lowest rate? Okay, all right. Mustafa, you almost got it there. All right. Okay. Now remember, the purpose of RTS and CTS is to make sure that everyone can hear them, right? Everyone can hear them. Everyone around the sender and the receiver can hear them. All right. So that they won't transmit, they would defer in order to avoid collision. So that's why you have to send it at the lowest rate so that everyone around the sender and receiver, even if they're far away, they can still hear the RTS and CTS, right? Because if you send at a higher rate, let's say you send at 2 megabits per second, there may be a hidden terminal that is outside the transmission range for 2 megabits per second, but still good enough for 1 megabit per second. That hidden terminal may not be able to hear the RTS or CTS, right? So, and it would transmit, that would cause a collision, right? So that means we have to send RTS, CTS at the lowest rate to accommodate everyone, okay? All right. Is that clear? Any question about that? Why do we have to send RTS and CTS at the lowest rate? Yes, so that all the hidden nodes can hear the RTS and CTS to update their network vector allocation vector, the NAV. All right. Okay. So it's similar to if, let's say, if I teach this class to you, and maybe there's a group of high school students. All right, a group of high school students. I may have to go very, very slowly so that high school student can understand, right? I have to explain more concept to them. I have to go into detail about modulation scheme because so that they can understand. So I have to go much slower, right? Much slower so that they can understand. Very similar. You have to send at a low rate so that the hidden terminals that are farther away from the sender and receiver can hear the RTS and CTS. All right. Okay. And because of that, because of the lower rate for RTS and CTS, you see here that we lose about 0.5 megabits per second for the overhead of RTS, CTS, and acknowledgements. Okay, we lose about 0.5 here. So, and if we use QPSK, we can have a good throughput until around 190 meters, right? But as soon as we reach 200 meters, the throughput will go down because of a lot of packet losses, and it reached zero about 240 meters. Okay, and you can see similarly for QAM16, right? QAM16 here, the distance is about I would say about 110 meters. Is the maximum should be 110. And then the QAM64 is about 70, about 70 meters. And QAM256 is about 40 meters, right? 45 meters, and that's it, okay? So you can see that the higher the data rate, the shorter the distance that we have to maintain in order to keep the lost packets at the minimum. All right, and that's the main idea of multi-rate transmission. The idea here is, depending on the distance between the sender and the receiver, we choose a rate that maximizes the throughput. Okay, so let's say if the sender and the receiver are about 200 meters away from each other, right? Then we should choose 1 megabit per second. Okay, 1 megabit per second. If they are about 150 meters away from each other, then we should choose 2 megabits per second, right? If they are about 20 meters from each other, then yes, we choose the highest rate, which is 8 megabits per second, all right? And that's the idea of these multi-rate transmission algorithm or protocol, okay? Depending on the distance between the sender and the receiver, we choose the optimal rate to maximize the throughput, okay? All right, so, and in order to do this, we need to estimate the channel quality, all right? Now, in this case, we assume that the channel quality determines by the distance, right? Of course, there are other factors as well, but the distance is the most important factor, right? So in this case, we assume that the channel quality is determined by the distance when we talk about this distance trade-off between the data rate and distance, right? But there may be other factors, and we'll see later how we take into account that kind of factor. All right, so basically we need to estimate the channel quality in order to determine the rate. The better the channel quality, the higher the rate. The worse the channel quality, the lower the rate should be, right? And the estimation should be accurate. It should be up to date. It can be destination-based or source-based, okay? So with RBAR is destination-based, and with ARF is source-based. So we'll see this later. And then the rate selection is based on predetermined threshold for transmission rate. And but we don't know the exact threshold because we don't know the exact channel quality. So usually we have to estimate, okay? And we see the estimation later. Okay, so let's talk about one algorithm first. And the algorithm is called auto rate fallback. Okay. All right, so it's called auto rate fallback. Okay. So let me get the text here. All right, so and this works depends on the number of acknowledgement received by the sender. Okay, so the sender receive acknowledgement and determines whether the channel quality is good or bad. All right. So if the sender does not receive acknowledgement for 2 consecutive packets, that means 2 consecutive packets are assumed lost, right? So that means the channel quality is not good. All right. So if it's lost, that means it's not good. That's why the receiver cannot receive correctly. So in that case, the sender has to reduce the transmission rate to the next lower rate. Okay. So we assume we have 4 rates, 1, 2, 5.5, and 11, for example. So if we are currently at 5.5, then we drop to 2, right? The next lower rate, and we start a timer. Okay, we start a timer. All right. So we'll see what the use of the timer later. All right. So now, if on the other hand, if the sender receives acknowledgement for 10 consecutive packets, right? So that means all 10 packets are acknowledged. That means the channel quality is good, right? So in that case, we can increase the transmission rate to the next higher rate, okay? We increase to the next higher rate. But if right after you increase to the higher rate, you get a packet loss, then that means it's not good. So you have to drop back to the previous rate, okay? You have to go back to the previous rate. So we increase, but if you have a packet loss immediately, then you have to go back to the previous rate, all right? So the concept is very, very similar to TCP congestion control, right? As soon as you get a packet loss, you go to a lower, a smaller window size, okay? Similarly here, if we get, as soon as we increase the rate, we get the packet loss, we go back to the previous rate. All right. So, and again, if the timer expires, right? So that is 10 consecutive acknowledgement I received. Now, if a timer expires, then we increase the rate as I said before. But if the next packet is lost, then again, we drop the transmission rate, all right? And we start the timer, okay? Now, why do we need a timer? We need a timer because if you wait to receive 10 consecutive acknowledgement, it may be too long because you may not send data that much, right? You may not send 10 packets. You may need to send 2 packets, and then you have nothing else to send, right? You have nothing else to send. And then you have to wait for a long time, and you send another 2 packets, nothing else to send. So it could take a very long time for the sender to increase the rate, all right? So that's why we say, okay, we have to set a timer. If the timer expires and we haven't sent 10 packets, we haven't received 10 acknowledgement, we can still increase the rate, okay? Otherwise, we may wait forever if we don't have much data to send, all right? Okay, and so this is one example of a ARF, okay? So in this example, we have 1 sender and 1 receiver, and they are on a line. So basically, the sender stay fixed and the receiver moving back and forth. Okay, moving back and forth at a rate of about 2 meters per second, if I remember correctly. So basically, the distance between the sender and the receiver varies as the receiver moves back and forth between to the sender or away from the sender. Okay. All right. So, sorry. So at the beginning, the sender start at very low rate. All right, it's a very low rate. And the plus signs indicate the packet sent. And then the x-axis indicate the time, right? And the y-axis indicate the rate. And these triangles represent the packets that are lost or not acknowledged, right? So we show them as lost. So you can see that we can have packet losses here, but the the sender starts sending. So it set a timer, right? Start at the lowest rate always, right? Just like in TCP congestion, we start at window size of 1. So we start at the lowest rate. And then it set a timer, okay? So you see when the timer expires, right? So this is when the timer expires. It goes to the next, rate, okay? And then it sends a sequence. And then when it goes to the next rate, it set a timer as well, start a timer. And let's see how many packets it sent. 1, 2, 3, 4, 5, 6, 7, 8, right? So you can see here, we haven't got to 10 yet, but the timer expires, okay? The timer expires. So the sender goes to the next level, okay? So when it goes to the next level, it lost 2 packets, right? So remember, So it lost 2 packets. And when it lost 2 consecutive packets, it had to drop to the previous rate. So it dropped to this, all right? And it's transmit 1, 2, 3, 4, 5, 6, 7, 8, 8 again, timer expires. Go to the next one. And when it goes to the next rate, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So it receives 10 acknowledgement for 10 consecutive packets, right? So it can go to the next level. So it goes to here, it's sending 1, 2, 3, 4, 5, 6, 7, 8. But the last 2 packets are lost, right? And when 2 consecutive packets are lost, and it had to go back to the previous rate, okay? Go back to here, 10, go back here to go up here. It lost 2. So have to go back to the previous level. These 2 are lost as well. So go back to this level, okay? And it continued to do so, right? Sorry. It continued to go here, and you can see here 1, 2, yeah, up to this point. And so you can see here 1, 2, 3, 4, 5, 6, 7, and then 7, and then there's a packet loss right here at this point. So that's why even it go 8, 9, 10, that doesn't count, right? Because we have to say that 10 consecutive packets, acknowledgement for 10 consecutive packets. But because we don't have 10 consecutive, it's interrupted by this loss. So that's why it have to keep going. And then at this time, the timer expires. So when the timer expires, it go to the next level. Sorry. And when it goes to the next level, it lost a packet, right? It go to this level, lost as well, all right? And so it stay at this level, okay? And so on. So that's how ARF works, okay? Any question about this? All right. So you can see that with ARF, the problem here is to increase the rate, you have to wait for the timer to expire, or you have to send 10 packets successfully. So it's not very adaptive, right? It's not very adaptive because the channel quality may be good around half of the timer here, right? Or maybe half of the packets here. But you cannot increase it. You have to send all 10 of them, or you have to wait for the timer to expire. So it's not very adaptive. So it takes a long time to detect changes, okay? If we go up a transmission rate and have not close to nothing to send, all right, we drop back down to array after timer expires. No, if we go up a transmission rate, all right, and you have nothing to send, and the timer expires, you can go to the next level. You go up to the next level, not drop down. Okay, you go up to the next level. So the timer is to go to the next level, to the higher rate, not to go down. Okay, the higher is to go to the next rate, not to go down. To go down, there must be packet losses, all right? So ARF, now ARF works, right? So it works. Whether it's efficient or not is a different story. It works. So it can adapt to changes in the network. It's as the estimate, the channel quality is estimated by the source. And the estimate is done using path acknowledgement, not on the channel quality itself, okay? And it takes a long time to detect changes, as we've seen before, okay? So Mustafa asked the question, does this always fluctuate like this forever or will it settle into a rate? No, it doesn't settle into a rate. Okay, oh sorry, I should take that back. It will settle into a rate if they don't move, the sender and the receiver don't move, right? If they don't move, they just stay stationary. Then yes, after a while, it will settle into the rate optimal for that distance, all right? But if they move, then this is what you have, all right? So you can see here, let's say here, this part here, or this part here, this is when they are close to each other, right? So that's why they can send at a high rate. But then this part here from here to here, that is when they move far away from each other, all right? They move far away from each other. That's why you have to get packet losses and then you go down, okay, in rates. So basically when you go up, that means they're moving close to each other. Going down, that means they are moving far away from each other, okay? All right. All right, so now, so this the disadvantages of ARF is it takes a long time to detect changes, 10 consecutive packets or timer. The estimate is done by the source, and it's based on acknowledgement, not on the actual channel quality, right? I mean, acknowledgement is an indirect measure of channel quality, but it's not a direct measure of channel quality, right? And again, the estimation should be done by the receiver, because the receiver is the person who receives the packet, right? So if the channel quality at the receiver is good, the rate can be high, can be set to a high value. If the channel quality at the receiver is bad, the rate should be set at a lower value, right? Because the receiver receives the signal, not the source, right? Why does the source determine the rate when the receiver is the person who received the signal, okay? All right, so now we go into receiver-based order rate. Okay, so with receiver-based order rate, this is the algorithm proposed in the paper. They use RTS and CTS for the algorithm, okay? So first, the sender sends RTS to the receiver. And in the RTS, the sender would record the size of the data. So let's say the packet size is, let's say 500 bytes, all right? And a tentative rate. That means the sender proposes a rate. And usually this rate would be based on a past successful transmission to the same destination, right? So let's say in the previous packet, in the previous successful transmission, the rate was set at, let's say, 2 megabits per second. Then the sender would put 2 megabits per second in here, right? So it's just a proposed rate, a suggestion. And then when the receiver receives this packet, it will measure the channel quality, okay? And it can measure the channel quality using, let's say, signal strength or signal to noise ratio, any metric, signal strength or signal to noise ratio. And depending on the signal strength, it will select a rate optimal for that signal strength, right? So now let's say it measures the channel quality and let's say, oh, the channel quality is good. I can go up to 11 megabits per second, right? Yeah. Or it may say the channel quality is bad, 2 megabits per second doesn't work. I have to go down to 1 megabit per second, right? And then it will send back the CTS. And it put the size of the data back, right, to 500 bytes, as we said before, for example. And the new rate, so let's say the new rate is 1 megabit per second. So let's say the sender proposes 2 megabit per second. The sender said, no, I want 1 megabit per second, all right? And then the receiver would use the rate selected by, the sender uses the rate selected by the receiver to send the data packet, all right? And then of course, the receiver would send back acknowledgement, right? So we skip the acknowledgement here, but the data would be sent at the rate selected by the receiver, okay? And this is the diagram we've seen before, right? So I'm just go briefly over it. Now in this diagram, we don't put DIFS or SIFS here. We just keep only the important data frame or control frames, all right? So the source, the destination. So A is a neighbor of the source, B is a neighbor of the destination, right? So when the source sends RTS, A hears the RTS. So it sets, it knows the, it set the nav to the value, the duration in the RTS, right? And then when destination send back CTS, B hears a CTS, would set the nav to this duration, right? And then this is the data, so the length of the data is L. And in the data, the duration is also set to indicate the acknowledgement, right? The length of the acknowledgement here. So anyone hear the data packet knows that it have to wait for the data packet. This length, D plus the acknowledgement, all right? Okay, so this is what we've seen before. Now, so this is a summary of what we said before about the new scheme, right? So the main idea here is we need to modify AO 2.11 a bit in order to implement the scheme we just said before, all right? So what do we need to modify? We need to modify the format of RTS, CTS. We need to modify the algorithm to compute the network allocation vectors. And we need to modify the data packet header. Okay, we need to modify data packet header. Okay. Okay, so first modification to RCS and TCS. So this is the original frame, RTS frame. Okay. So it has the frame control information about the frame. For example, indicate that this is an RTS frame. It has a destination address, source address, and the duration. Okay, duration. And so the duration here in the original RTS frame, the source, the sender would calculate the time for the CTS, the time for the data packet, the time for the acknowledgement, add them together, plus the SIFS as well, right? And then put the duration in here, okay? And this is a frame check sequence to check for the integrity of the whole frame, right? So let's say to use a CRC, for example. Now, the modification here is instead of putting a duration, a specific duration, now the sender, the source would put the proposed rate, okay? Let's say it proposes 2 megabits per second. And the length of the data packets, right? Let's say 500 bytes, all right? So that every knows that here, this RTS can use the rate and the length to calculate the duration, right? You can calculate the duration using the rate and the length. Similar for CTS, again, CTS has a duration, but now we replace the duration by the rate and the length. So now the rate is the rate that the receiver proposes. Basically, let's say 1 megabits per second instead of 2. And the length, it's copied this length to here, all right? Okay, so now, and when the receiver receives the RTS, right, so it can measure the signal strength or the signal to noise ratio of the RTS. And from that measurement, it determines the quality of the channel, whether it's good or bad. And here we have some kind of threshold, right? So if the signal strength is this number of decibel, for example, then you can use this rate. This value, you can use this rate, right? So there's some kind of algorithm there. So we're not going into the exact detail, but just to let you know that you can use signal strength or signal to noise ratio. All right, so that's one modification. Now the second modification is here is, you see here in the RTS, right? the source proposed a rate, okay? And then the destination changes this rate, right, to a different rate. But when the destination sends the CTS back to the source, A may not hear the CTS, right? Because A may be far away from the destination. A may not hear the CTS. So that means A only has the information in the RTS, but this information now is old, right? The rate has been changed. How can A know about this new rate, right? So this was 2 megabits per second. Now this becomes 1 megabits per second in the CTS. How does A know that the rate has been changed? Okay, so there must be a way for the algorithm to tell A that the rate has been changed, right? The rate's been changed. Okay, and this is done by, and this is the example I just said before. Now assume here, the source say 2 megabits per second. Based on 2 megabits per second, A calculates the nav, right? And this is the nav here. And then the destination change it to 1 megabit per second, okay? So you see, if you have 1 megabit per second, the duration is longer, right? It's no longer 2 megabits per second. So what it means is now A has the wrong nav, right? The wrong value. And it may transmit at this point, right? It may transmit this point, and that packet will collide, right, with the data packet here, for example. All right. So that's why there must be a mechanism for the algorithm to tell A that the previous information is now obsolete. You need to use the new rate, which is 1 megabit per second. All right. All right, so to answer Samyak's question, is SIFS not shown here? You're right, it's not shown here. Okay, we want to simplify the diagram because in this diagram, SIFS is not important. Okay, right. All right, so now we'll talk about the mechanism to let A know that the rate has been changed. Okay. All right, so in order to do that, we add a reservation subheader to all the data packets. Okay, so we add a reservation subheader to the MAC header of all the data packets. Okay, and you can see here, if the source now have the new rate information in here. All right, so basically the correct rate information is now in the data packet. Okay, so 1 megabit per second, or the length of the duration, the new duration would be here. Then A can hear this data packet, and it knows that now the nav have to be changed to a longer value. All right, so that means we put a reservation subheader to the MAC header of the data packet. All right, and then when A hears this data packet, it will check the reservation subheader, and it sees the new duration, and it will adjust the time to the new duration in the reservation subheader. Okay, so before it gets information from the RTS, but this may be wrong. Okay, now it will get the most up-to-date and accurate information from the reservation subheader, and it will wait for this amount of time. All right, so it had to modify the nav to allow the updates. Okay, all right. Okay, so how do we add the reservation subheader to the MAC header? So this is the original MAC header. All right, so the data frame. So it has the frame control, right? Duration. So this is a data frame, the original data frame. It has duration, destination address, source address, the ID of the basic service sets, and the sequence control. And then this is the body of the data, basically the data in here, and then the frame check sequence for the whole frame here to protect the integrity of the whole frame. All right. So this is the duration. Now, in the new scheme in RBAR, what we do here is we will separate the frame control, duration, destination address, source address. We separate this part, all right? And we put it in a reservation subheader. We call it reservation subheader, all right? Now this duration here, it will be changed by the sender. It will be updated by the source to indicate the new duration based on the new rate suggested or proposed by the, or selected by this destination, okay? So this new duration is the new duration calculated based on the selected rate from the destination, okay? And then, sorry, why I'm sure I keep moving. And then we need to add another checksum. Okay, so this is a frame checksum. And we add another checksum to protect the subheader, the reservation subheader. Okay, so this header checksum, it protects this part. And this frame check sequence, it will protect this part. Okay, or it can protect everything, that's fine as well. But we need to, oops, sorry. We need this new reservation subheader, sorry, the header checksum to protect this part, okay? Why do we need this part? And why do we need to separate the reservation subheader? Why don't we just change the duration here? Okay, why don't we just change the duration here to the new value? Why do we have to make things more complicated by creating a new reservation subheader? Okay. The reason is that the reservation subheader, this part, okay, this part must be transmitted at the lowest rate. Okay, so again, this part must be transmitted at the lowest rate. Okay, and the rest can be transmitted at a higher rate selected by the destination. All right. So assume that the destination selected 5.5 megabits per second, right? Then we can send this part at 5.5 megabits per second, but the reservation subheader must be sent at 1 megabit per second at the lowest rate. Okay, why? Why does it have to be sent at the lowest rate? Anyone? We already talked about this before. Okay, yes, there's an answer from Marie-Louise to accommodate far away nodes, exactly. So that everyone can hear, can decode at least the reservation subheader. All right, everyone can decode the reservation subheader to accommodate the nodes that are far away. All right, so that the hidden terminal, basically the hidden terminals, all the hidden terminals can read at least this part to know the new duration in order to update their nav, right? Exactly the same reason why we send RTS, CTS at the lowest rate. And you can imagine this as a new CTS, right? This would be a new CTS as well, or a new RTS as well, to let everyone know the duration of the data, the transaction. Okay, so that's the reason to accommodate everyone, all the hidden terminals in the network, right? Okay. All right, and because of that, because of transmitting at two different rates, this at the lowest rate and the rest of the frame may be at a higher rate, right? They may be the same or they may be different, all right? But it may, this part may be at a higher rate. This part may be, this part is at the lowest rate. And because of that, at the physical layer, we have to modify the header of the packet at the physical layer as well, right? So at the physical layer, this is the original packet header, right, of the packet at the physical layer. There's a part with the length of 1 byte where we put the signal. Basically, it's the modulation scheme or the code of the modulation scheme that determines the data rate of this packet at the physical layer. Now, instead of putting the signal, the scheme, the code for the modulation scheme, we divide this into 4 bits and 4 bits, and we put the rate that we sending the data, the rest of the packet, basically the rate at which we send the rest of the packet, and the rate at which we transmit the reservation subheader. So we put it here, all right? So, and at the physical layer, the physical layer will have to switch rate, right? One rate to send the MAC header, sorry, not the MAC header, the reservation subheader, and one rate to send the data, okay? So let me change this here. One rate to send the reservation subheader. Okay, the reservation subheader, sorry. Okay, and one rate to send the data. Okay, all right. Okay, and if we do that, then this is the new diagram for RBAR. So we still send RTS, CTS, but the data now has a reservation subheader at the beginning. Okay, and don't forget it has to be sent at the lowest rate here, the reservation subheader. Okay. Yes, we'll have a quiz very soon. Okay, so I'll just finish it and then we have the quiz. And then every node that can hear this reservation subheader, they have to adjust their nav to this new value. Okay. All right. So this is a summary of RBAR, and then when we come back, we talk about the experiments. So RBAR is more accurate because the estimate is based on more accurate information, which is based on channel quality at the receiver, and it's based on signal strength or signal to noise ratio. It's not based on acknowledgements. It's closer to the actual transmission, and it can be implemented in AO 2.11. However, the AO 2.11 now becomes more complex because we need to add a reservation subheader, and we need to add a checksum for the reservation subheader, and the MAC header now have to be sent at the lowest rate. Okay, so that all the hidden terminals can hear the new duration. Okay, all right, so let's have the quiz, and then we continue with this. Okay, so please open eClass. Let me go to eClass here. Then I'll make the quiz available. Okay, so if you go down at the end of the page, to the very end of the page, you will see quiz 5, ATCP. Okay, anyone, so can everyone see that? Anyone who has not been able to see the quiz? Okay, all right. Okay, so let me give the password on the window. Okay, 1 second. Okay, so this is the password. Type the password. Okay, so we'll be back at 3:50. Okay, so you do the quiz and take about, oh sorry, 3:55. Yeah, 3:55. Okay. Okay, so after the quiz, please take about 5-minute break, and then we'll be back at 3:55. Okay, yes. Okay, so I'm back. So are you able to see the mark of the quiz? Okay. All right. There's a question from, okay, great, thanks. From Ruchit, that so the quiz started at 3:43, right? So the quiz started at 3:43, and so at 3:53, I stopped the quiz. All right. So if you had 4 minutes left, that means you started late. But it started at 3:43. Okay, so and then at the 3:43, and at 3:53 I stopped the quiz. So you must have started late. Okay, right. So okay, so let's continue the lecture. So for RBAR, we have just a little bit left, which is about the experiment to compare RBAR. Okay. Let me share. All right. Oh, sorry. I think I should share the other way so I can. Okay. So all right. So now we compare ARF with RBAR, right? So just a quick recap. RAF is based on acknowledgements. Depending on the number of acknowledgements not received or received, we increase or we decrease the rate. With RBAR, the receiver measure the signal strength from RTS and propose a new rate in the CTS. Okay, so and we've said that RBAR should be better. So now we do some comparison. Okay, so in one configuration, we have only one single connection between two nodes. One node is fixed, stationary, and the other node moving in a straight line at 2 meters per second. And we assume Rayleigh fading channel. Okay. And then, so we'll talk about the first configuration first. Okay, and this is the result. Okay, for that first configuration. Okay. So the first graph shows the signal to noise ratio as the time lapsed, right? So we go from let's say 130 to 130.05, for example. And this is the signal to noise ratio. So when we have a high value here, it indicates a good channel quality, and if we have a low value here or maybe a low value here, it indicates a bad channel quality, right? And okay, and this graph here is for ARF, and we've seen before, right? So this is the time and this is the rate based on the number of packet losses. So the losses are indicated by the triangles. So we've seen this before, right? So now we consider the scheme, the rates by the set in RBAR. Okay, so you can see that the first observation is that with RBAR, the number of packet losses is much lower, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 packets lost. Here we have only 2, all right? And the reason is that with our ARF, we increase the rate, right, to a high rate. And because of the high rate, we have packet losses, and that's when we reduce the rate, right? So that's why we have many packet losses. With RBAR, we measure the channel quality, the current channel quality at the receiver. So that's why that leads to packet losses. Okay, and you can see that. Excuse me. Sorry. Yeah, please excuse me just for one for about 10 seconds. Yeah. Okay, yeah, sorry. So I'm back. Sorry, just 1 second. Let me raise the desk. Okay. All right. So I just needed, sorry, I needed to raise my desk. Yeah. So you can see with RBAR, the rate, you can see the rate here follows very closely with the signal to noise ratio measured at the receiver. Right, so you can see here the low point here is correspond to this low point here, and then the high point here correspond to the high point here, right? The low points here and here, the low points here, and the high point here equivalent correspond to this part here, right? So you can see that the rates set by RBAR follow very closely with the signal to noise ratio measure by the receiver. Okay, so that's why we can have first very low packet loss rate, and secondly, most of the time RBAR spent at higher rates, right? So you can see a lot of packets sent at a higher rate here, right? Compared with only these from ARF, and the same for the second highest rate here. Okay. And this shows the the throughput, the mean average throughput of ARF and RBAR. Now the dotted lines represent the ideal throughput for the fixed rate, right? So we've seen this diagram before. If we just focus on the dotted lines, okay? So this is the ideal rate and ideal distance for QAM 256. And the last one here, which is the ideal distance and ideal rate for binary PSK, right? Quadrature PSK, QAM 64, and this QAM 256, all right? So that's the the fixed rate, okay? Now, and under ideal condition, right? Now for ARF, which is the solid line here, right? So you can see that ARF at the highest rate, it follows very closely with the fixed rate. But as the distance between the source and the receiver or the destination becomes larger and larger, the throughput of ARF is much worse than the fixed rate, right? The throughput, because of many packet losses, right? And we can see from here, right? Many packet losses. And if you lose packets, then the throughput will go down. Okay, so that's why you can see, compare with, let's say, compare with this, at this distance, the throughput of ARF is much lower than that of QAM 64, right? Lower than QAM 16, lower than quadrature PSK, lower than binary PSK. Now RBAR is better than ARF. If we look at the lowest rate, it follows very closely with 1 megabit per second, 2 megabits per second, 4 megabit per second, and then 6 megabit per second and 8 megabits per second, right? But you can see here that at the highest rate, the throughput is lower. The throughput of BAR is lower than fixed rate or even ARF, okay? So I'll just leave this as a question for you to find out. And the answer is in the paper, right? I'm not going to answer everything. So the question for you is why RBAR performs worse than ARF and at the highest rate, okay? So it's in the paper. Look in the paper and next time, please remind me, and then I want to hear the answer from you, at least one of you, okay? Right, so, but this diagram shows that RBAR performs better than ARF in most cases in terms of average throughput, okay? And so, and this is the throughput, again, vary based on, so in this case, vary based on the distance, right? The distance or the channel quality. Here, the same experiment, but we vary the average mobility speed. That means the nodes will be moving. So in this case, we still have 2 nodes on a straight line, and we the sender is fixed, the receiver is moving toward the sender and then far away from the sender, back and forth, and we vary the mobility speed of the receiver. So between 2 and then 4, 6, 8, and 10, okay? And we measure the average throughput. So you can see that among all of these, RBAR is the best performer. It has the highest throughput. And then ARF has the second highest, all right? And then the next is QAM 16 here. QAM 16 is here. And then the next is quadrature PSK is this one. And the next is QAM 64. The last one is binary PSK, and this one is QAM 256, all right? So the first observation is that as the mobility speed increases, the throughput is going down. Okay, and that makes sense because as mobility speed increases, we may lose more packets, right? We may lose more packets because let's say the receiver send back an RTS proposing a rate of, let's say, 11 megabit per second. And then before the source can transmit the data packet, the receiver may move far away from the source, right? So the data packet may be lost because at that point, the receiver will move far away from the source. Okay, so you can see that's why as we increase the mobility speed, the throughput going down because we will have more packet losses. And the surprising thing is the highest rate here, QAM. It's not surprising if we can find a reason. QAM 256 had the second lowest throughput. All right. And again, the reason is because if we send at the highest data rate and they are moving, and when they move far away, we would lose many packets. And because of many packets were lost, that's why the throughput is going down, right? When we say throughput, that means we only measure the packets correctly received. And again, if we use the lowest rate, then the throughput is the lowest for sure, right? So basically the lowest rate and the highest rates give us the worst performance, okay? So in the second graph, the configuration is this one here. We have a network of size 1500 times 300 meters, and we put 20 nodes in there, and nodes move randomly using this random waypoint mobility pattern. And we randomly choose the speed for different nodes at 10 plus and minus 10% of the mean speed or average speed, and we vary the average speed between 2, 4, 6, 8, and 10 meters per second. And we use DSR routing, right? We learned DSR before. And we choose two nodes, one to be the source and one to be the destination. And if we do that in this network, as before, we vary the average mobility speed, and we measure the throughput of the source and the destination when they transfer a file. Then you can see that RBAR has much higher throughput than ARF. Okay, again, because it adapts, it has more accurate channel quality estimation, and it selects the optimal rates for that channel quality, the current channel quality condition. Okay. All right, so this is a summary of RBAR, right? So multi-rate transmission can increase throughput, as we've seen from this graph here, right? Both ARF and RBAR, they are perform better than fixed rate. Okay. The receiver can estimate the channel quality better than the sender, for sure, right? And the closer the estimate is to the channel quality, the better the estimate. And RBAR adapts to changes in channel quality quickly, much more quickly than ARF. Okay. All right. So any question about this? Okay. Any question about RBAR? And these are the papers. So I posted the paper on eClass, so you can read the paper for more detail. Okay. All right. So now let's go to cellular network. So again, for cellular networks, the textbook is on reserve in the library. And tomorrow, the TA, the grader, the marker, the TA marker, Honda will be the marker. He will bring the midterm test papers in the lab, and he'll be there. If you want to pick up the midterm test paper tomorrow in person, please go to the lab and pick it up from Honda. And if you have questions about your grades, please talk to Honda tomorrow. Okay. Right. So let's continue with the cellular networks. Okay. All right, so this set of slides is from chapter 3 in the textbook. So it's this textbook here, right? I said I have it put on reserve for 24 hours per person. All right, so we'll talk about the components of a cellular network. We talk about frequency reuse and planning, the hexagon grid, distance to reuse ratio, call handoff, and the maps used in network design. So basically, this lecture is it's about practical knowledge about cellular networks. In a cellular network, there are 5 key components. So the mobile phone, right? For sure, mobile phones would be the most important part there. And then we have base stations, and we have a backhaul network, also called a fixed network. And we have the core network, and we have the interconnection to the public switched telephone network and the internet, right? And this is a diagram of the cellular network, right? We have the components. So first one is the mobile phone, and then we have the base stations, and the base stations are connected together and connected to the core network, and so these base stations are connected and then connected to the core network as well. And we call it the fixed network or the backhaul network. And then we have the core network, or we also call the mobile telephone switching office, MTSO. Okay, and this will be connected. This core network will be connected to the internet and also to the landlines, the telephone network landlines, right? So not many of us are using a landline these days, but we still have those lines, especially if you use internet. They can reuse those lines as well for the internet, right? But this will connect it both to the internet and the landlines network. Okay. All right. So the mobile phone. So basically, each mobile phone has the ability to process millions of calculations per second in order to compress and decompress the voice stream. And these days, it also be able to process data as well, data tasks as well. Okay. So these days, the traffic is on in digital format. Voice, data, images, video, everything is on digital format, but the transmission are sent through the air, right? And they are being transported as analog signal on a specific frequency, right? And the scheme that we've seen before, when we talk about phase shift keying, amplitude shift keying, basically that's how we convert digital data into analog signal, okay? And that's how it works in a cellular network. And the other way around, when we receive analog signals, we have to convert it back to digital data, right? And these are the components of a cell phone. So we have a digital signal processor. So we have a microprocessor and control logic. So basically, this is equivalent to a computer, right? The microprocessor on a computer. We have digital to analog and analog to digital conversion component here. The memory, just like in a computer. Power from power management and charging, radio frequency modulation, for example, and amplifiers from and to the antenna on the phone, right? So these are the basic components of a cell phone. I'm pretty sure that if you are in engineering, you already know all of this, even better than me. So the next component is the cell base station. The cell base station is the physical location of the radios, also known as transceiver, to send and receive signal from and to the cell phone. It also accommodates equipment cables and antennas that serve subscribers. And usually we mount cell-based stations at a high location like towers or rooftops. So the common location are towers or rooftops. And then the backhaul network is also called the fixed network, which is a web of circuits. Basically, we connect the base station to each other. So it connects on cell-based station to the cellular core network or the mobile telephone switching office, as we've seen before. And basically, it connects subscribers to the outside world, right? It goes through the switching office, and from the switching office to the internet or to the landlines. So the core network, basically the core network is this part here. Sorry, this diagram here, right? Core networks, all right. So this belongs to the carrier. So let's say if you have Telus, you have Bell, you have Rogers. Each of them would have their own switching office and core network. Okay. All right, so basically it's a large building. A core network or the switching office is a large building which houses the switching equipment, and it manages active phones and transmissions. It monitors base station and network elements. So basically it controls the operations of base station and phones and subscribers' phone, and it supports routing. Basically, yeah, we know what routing is. We connect call and data transmission by switching conversation and digital data packets from network path to another. So it performs routing. And then we have the interconnection and the links. So basically the internet connections of the subscriber through the switching office to the public switch telephone network and to the internet. So these interconnections are high capacity circuits between the wireless and the landline networks. And it connects wireless call to the landline public network. And it allows landline caller to reach a mobile subscriber, right, two ways, from wireless network to the landline network, and from landline networks to the mobile phones. All right, so there's a concept in cellular network which is called population count, or POPs, right? And one person equal to one POP count, all right, one head count. And wireless markets are bought, sold, and valuated and traded based on the basis of POP counts. For example, if you have, let's say, assume that now Telus want to sell their network to, let's say, Rogers. So the value depends on the number of subscribers, right? The more subscribers Telus has, the higher the asking price can be. It also based on the density as well. So basically, if you have a very high density network, that means you have a lot of subscribers within a small area. Again, the value of that market is higher than if you have a sparse network, all right? So in practice, wireless markets are traded using POP counts. Okay, so let's talk a bit about the base station. Okay, so this shows the communication between a cell phone, a mobile device, and the base station. So usually there are two channels. One is downlink, the other is uplink. So the downlink is for the base station to send data or control information to the cell phone. And from the cell phone, it can send data to the base station, voice or data, and this is called the uplink, all right? So the downlink is on the forward channel and the uplink is the reverse channel, okay? And it's easy to visualize. We say downlink because the base station is high, so it's going down from the base station to the phone, and uplink from the phone to the base station. And another concept in cellular networks is channel spacing. And channel spacing refers to the actual bandwidth space allocated to every wireless channel out of the total amount of spectrum allocated to a carrier, all right? Here we use FCC. This is the US. In Canada, we have a different organization. I think it's CRCT. Yeah, I don't remember exactly, but it's equivalent of FCC in the US. So this book is written by an American author, so that's why they use FCC. For example, AMPS. This is the Ondas Air Interface. It was designed by Bell Labs for the US market, and it's considered as the first generation of cellular networks. It's an analog cellular network. It's based on completely on analog, only for voice. It was only for voice. The channel spacing is 30 kilohertz, right? 30 kilohertz for uplink and 30 kilohertz for downlink, right? So basically, this is 30 kilohertz, and the uplink is 30 kilohertz. Okay. In GSM is the second generation of cellular networks. So the spectrum is divided into 200 kilohertz carriers, and each carrier then allocate 25 kilohertz to the uplink or downlink, right? So that means you can have 25 kilohertz here, 25 kilohertz to the uplink, right? So, and the reason they have these because they use frequency division multiplexing, right? Frequency division multiplexing. Or they can use time division multiplexing as well. They can have a, this channel, let's say 30 kilohertz, and then each subscriber gets a time slot on this channel, okay? So basically this is both frequency and time division multiplexing. The frequency is divided into the uplink and the downlink, right? Each is 30 kilohertz. This is where we have frequency division multiplexing. And then within each frequency, we can divide the frequency, that channel, into time slot, and each subscriber got a time slot there. So we combine both time division multiplexing and frequency division multiplexing. Now, CDMA is different. Code, so this is based on code division multiplexing. So in this case, all subscribers share the same channel, all right? And the spacing is 1.25 megahertz, okay? Because all subscribers share the same channel. So in the next lecture, we'll learn about CDMA, how to encode different calls so that all of them can share the same, many of them, a large number of subscribers can share the same channel. Okay, so we'll learn that in the next lectures of CDMA. Okay, so any question about channel spacing? Okay. So now we're talking about frequency reuse and blending in the past, right? So this is no longer used in today's networks, but many of these concepts are still carried over to the current network, okay? So in the past, when we have, let's say, frequency division multiplexing, very, very often, all the time, we reused frequencies, okay, to support concurrent transmission, because there was a limited spectrum. So the same frequencies are used over and over again throughout the network, okay? And there are 416 pairs of channels distributed throughout the 7-channel frequency reuse plan. So if we take a look at this diagram here, you can see that there are 416 channels. So they are divided into 7 frequency bands, all right? And within one area like this, you can use you can use 7 channel bands at the same time, right? Because they do not interfere with each other. So 1, 2, 3, 4, 5, 6, 7, right? And then you can reuse these frequencies in another section, right? So now you can see 7 and 7, they are separated by a very large distance. So that's why, even though they have the same frequency, but they are very far away from each other. So they did not interfere with each other, right? 7 and 7 here. Similarly, if you have 1 here and 1 here, they use the same frequencies, but they were very far away from each other. So they do not interfere. So these 7 channel bands will be reused throughout the whole network. So that's where you have a limited spectrum, but because we divided the network into cells like this, and we reuse this, the same frequency for cells that were far away from each other, we can reuse the frequencies, all right? And high traffic cell would have more radio channels assigned to them, all right, based on subscriber density. For example, if we have, let's say this is downtown Toronto, so you can have more radio channels here so that we can support more users. And this is, let's say, up in, let's say, Thunder Bay, right? It's very sparse there. The population is very sparse, so you can have less channel, radio channels, for example, to support less subscriber there. Okay, so now this scheme is no longer used in practice today, all right? But this is what was done, what was implemented in the past in order to use a limited set of spectrum over and over again throughout the network. So today we use CDMA, code reuse. Okay, so next time we'll learn about CDMA, then we know how we can use it. And we also use something called automated frequency planning tools. And the tools will assign frequency based on, geographic frequency allocation based on interference avoidance algorithms, geographic data, and market size. So it's basically, it's a very complex algorithm to allocate frequency based on all of these factors. Right? So we're not going into the planning here. But to let you know that they have planning tools, basically software, in order to assign frequency based on these factors. Right. So yeah, and then when we talk about this kind of frequency reuse clusters, right, or cell, it's also related to something we call the hexagon grid. Okay, the hexagon grid is something like this. Right, so you can see we have these hexagons, just like in the previous diagram. And if you have the base station here, right, then the transmission range of the base station would extend over a circle like this. Okay, over a circle like this. And then different base station would have different circle. Now, but there are always overlapping sections like this here, these overlapping sections. And these sections are very important. It allows a receiver, a subscriber, to move from one base station to another. So let's say when we are driving on the highway, right? If we are leaving this base station, we go into this overlapping area. In this area, we are prepared to hand over from this base station to this base station, for example. Again, if we're continue driving on the highway, we go into this overlapping area, the handover or handoff happens here, and then we move to this base station, okay? So this is the base station, and the circle around it is called the coverage area or cell, okay? All right, so yeah, and the overlapping cell coverage is important. It's needed for call handover or handoff. Of course, handoff cannot occur unless there's some kind of overlapping, all right? Now the size of each hexagon depends on the subscriber density. So if let's say in downtown Toronto, the subscriber density is very high, so the hexagon could be smaller, right? But in a rural area, the subscriber density is low, so you can have a larger hexagon in order to accommodate a larger area. All right, so these are the uses of the hexagon grid. So basically, it was used to eliminate signal interference, right? For long-term frequency planning. So where to put the next base station, for example, right? If you have this already, where would you put the next base station? Of course, it have to be somewhere here, right? Or here. So that can be overlap between these, or maybe one here, right? So allows for addition of new cell into a wireless market. Yeah, again, just to make sure that it overlaps with existing coverage areas of other base stations. It allows mobile phones to hand off given a cell system, identify co-handoff candidate cell for every given cell in the system. And it can be used for traffic analysis purposes as well. All right. So now these days, the hexagon grid is no longer used formally in system design and planning, but the concept is still used when we talk about cellular networks. Okay, when we talk about cellular, we still use these concepts. Another, okay, so let's see, there's a question here. Oh, handoff here mean, okay, so the question is, what does handoff mean? Handoff mean a mobile phone moves from one base station to another base station. All right, one mobile phone moves from one base station to another base station. So at this point here, it will be controlled by this base station instead of this base station. Right. So when we drive over on a highway, that would happen. We move out the range of one base station and move into the range of another base station. Okay. So that does that mean by handoff from one base station to another. All right. So the next concept is distance to reuse ratio. So the distance to reuse ratio is the geographic distance between cells using identical frequency in order to avoid interference between the radio transmission in these cells. Okay, so remember this example we had before when we have 7 channel bands or channel spectrum, and we need to allocate them to these cells, right? So we have to, if we use channel frequency 5, for example, and we reuse it here, the distance must be far enough so that they don't interfere with each other, all right? And this distance here is called distance to reuse ratio. Okay, so they have to be far enough so that they don't interfere with each other because they are using the same frequencies. And this distance to reuse ratio is determined by the geographic coverage size of cell base stations and the radio power level used at cell base station transmitting the same set of frequencies, right? So it determines by the size of these, right? And also by the power level. So they must transmit at a level so that it only around this area and only around this area so that they don't interfere with each other. Okay, so that's the main idea of distance to reuse our frequencies. Okay, and these days, this distance to reuse ratio is computed by software of propagation analysis tool, okay, by the software for doing that. So we need this software when you build a network and then you put a base station here. And now you must decide where to put this base station so that they can use the same frequencies and they don't interfere with each other, right? And that's where we use the software to do the calculation to determine this distance here, okay? Right. So the next concept is frequency agility. All right, so frequency agility refers to the capability of mobile phones to operate in any frequency in the carrier assigned radio spectrum. Okay, so basically a mobile phone should have the ability to change frequencies instantly. When we say instantly, mean in milliseconds upon command from itself, right? Based on the signal strength test of wireless system, based on command from the wireless system. Either the base station tell them to change the frequency or from itself. For example, in this diagram here, right? You can see that this base station is using frequency 5, and this one is using frequency 1. So when a mobile phone is moving from this cell, right, to this cell, it should be able to change frequency from 5 to 1 in milliseconds. So that there's no interruption in the service, all right? And that's the ability of mobile phone to change frequency instantly is called frequency agility, okay? All right, so, oh yeah, so the question about call handoff here. The call handoff, again, is the process of a mobile phone transfer from one cell to another, right? So moving from one cell to another, and while changing the frequency as well. It's also sometimes called call handover or call handoff. Both are equivalent, call handoff or handover. Okay. All right, so the mobile phone will monitor the signal level itself, okay? And when the signal from the current cell is weak, it can scan the control channel signal from all the neighbor cells, from all the neighbors' base station, all right? And then it requests a call handoff with the strongest station. So if there's a station that has the strongest signal, then it can send a request to join that cell, that's base station, okay? And overlapping radio coverage allows for call handoff to occur, and it's controlled by the microprocessor. So if we go back here, you can see in this diagram here, right? So these areas here, the overlap between cells allows nodes to scan for a cell that is that give the phone the strongest signal. And when it determines that the base station with the strongest signal, it sends a request to join that base station. Okay. Right, and so this is the main idea we just talked about. So this car here is in between the two base stations, right? So you can imagine this area is the overlapping between the coverage areas of station 2 and station 1. So this car can determine the base station that had the strongest signal, maybe this one here, and it can request to join this base station, okay? And then the concept of handoff, as I said before, when it moves from one base station to another, right? There should be some overlap here, but the main idea is it moves from one base station to another. Okay, so so frequency reuse and frequency agility allows a carrier to use a small amount of radio spectrum to support many wireless, many subscribers, right? So they have a very limited amount of radio spectrum, but because they reuse a frequency, and cell phone can switch frequency very quickly, instantly. So that's allowed for carriers to use a limited small amount of radio spectrum to support a large number of subscribers. And frequency reuse, frequency agility, and call handoff are the technology that makes cell phone technology a reality these days for us, right? So it's funny because I was watching an episode of Seinfeld last night. I'm not sure, maybe you are too young for that series. The series is called Seinfeld. And there's an episode in which the group of friends, there was chaos in the group because they didn't have a cell phones at that time. They were trying to coordinate with each other to see a movie together after work, but they couldn't because they didn't have cell phones. And it was very funny because something we take for granted, like cell phones these days, but back in those days, in the early 90s, yeah, it was a chaos. It was very funny, but that makes us appreciate technology even more. Okay, so another concept, I think this is the last concept, which is maps. So originally, topography maps were used in cellular system design, for sure, right? Because remember, we've seen those hexagon before, the hexagon grids as well. Sorry, one second, please. So we've seen the hexagon before. There must be some kind of design and planning in order to know where to build the base stations. So that the coverage could be overlapped, and then at the same time we can have frequency reuse as well. So and on cell site location are denoted using the polar coordinates like latitude and longitude in those maps. And in those days, wireless system engineers needed to learn how to read the ground elevation on maps and the overall map symbology, basically the symbols on the maps. For example, they must be able to distinguish between mountains, airports, rivers, oceans, for example, so in order to decide where to build new base station, where to set the coverage area, for example. So today we have software version of the topography maps, right? So we don't use like paper maps anymore, but in the past, the engineers had to use the maps on papers, right? But these days we will have software to do these tasks. All right, so that's the end of this lecture. So again, this is a very light introduction to cellular networks. Okay, so next week we'll continue with the topic, but we go into radio frequency technologies for this, right? Okay, so I will stay for in the next 5 minutes if you have questions. All right, so otherwise, thank you everyone for participating in the lecture today. And I'll see you either tomorrow in the office hour at 1 or next week. Okay, and just hope that there won't be a strike. Okay, all right, so yeah, so I'll stay, yeah, finger crossed. All right, thank you, Mary. Yeah, you're welcome. Thanks, Paul, you're welcome.